This lesson is about solving inequalities with absolute values. First, though, let's remind ourselves what an absolute value is. For example, the absolute value of -7 is 7. And while it's tempting to think of absolute values as negative sign removers, it's better for the purposes of this lesson if you remember that the absolute value of -7 means its distance from 0 on a number line. -7 is 7 spaces away from 0 on a number line. So here is a problem that we'd like to solve. It's an inequality. It has an absolute value in it. But before I show you the techniques for solving this, I'd like to do a little trial and error first. So first, let me pose the question, is x equals 3 a solution to this problem? Well, to find out, I'm going to plug 3 in for x into the problem and see if I get a true statement. A little bit of arithmetic here will show that I do in fact get a true statement because 1 is less than 3. And because 1 is less than 3, x equals 3 is a solution to this inequality. But it's not the only number that's a solution. I've also discovered that x could be 1.4. Sort of a random number I picked. Watch why 1.4 is also a solution. If I replace x with 1.4 and do some arithmetic, I will also get a true statement. 2.2 is less than 3, therefore 1.4 is also a solution. Now I've showed you that 3 and 1.4 are examples of solutions to this inequality, but they're by no means the only two. And we don't want to solve these by guess and check, so let's examine a strategy that will enable us to find all of the x's that are solutions, not just random ones that we try. Here's a good strategy. I think we'd all agree that x is some number or can be many different numbers, and we don't know what it is. But if x is a number, then 2 times that number minus 5 is also a number. The absolute value of that number means its distance from 0. And so this inequality is saying that that distance is less than 3. So 2x minus 5 is some number whose distance from 0 is less than 3. In other words, it must be within 3 spaces of 0 on a number line. So here's my number line. Here's 0. 2x minus 5 must be within 3 spaces of that. Well, within 3 spaces of 0 are these two regions in red. Restated, 2x minus 5 could be here because the distance between that and 0 is less than 3. 2x minus 5 could be here because the distance between that and 0 is less than 3. Likewise, 2x minus 5 might be here, 2x minus 5 might be here. It, however, cannot be here because that distance from 0 is greater than 3. Likewise, it can't be here. Well, all these thoughts lead to the following string of inequalities. Now, in case you're not familiar with this double less than notation, this is effectively a between statement. And to clarify this for you, let me take a break from this problem and present you with a kind of silly scenario. I want you to imagine a baby, yourself, and a centenarian. And imagine their ages. A centenarian, by the way, is someone over 100. Now, if we were to put these three individuals on a number line from youngest to oldest, obviously, this is what we would have. You, your age, would be between the baby and the centenarian. I think we could all agree that this is true for you, but likewise, this is also true. In other words, the baby is younger than you, and you are younger than the centenarian. If I were to put these two inequalities together and form a single string of inequalities, it could be read the baby is less than you, and you are less than the centenarian. But equivalently, wouldn't that be the same as you're between the other two? In that sense, we think of this double less than notation as a between statement. Algebraically, this statement here can be thought of as 2x minus 5 is some number between negative 3 and 3. Now, let's go to the actual algebra of solving for x. In order to solve this for x, I have to get the x by itself. And to do that, I'm going to add 5 to all the quantities in this string of inequalities. By adding 5, I will cancel out the negative 5 that's there now. In my further goal to isolate the x, I'm going to divide every number in this string of inequalities by 2, thereby isolating the x. Now, one way to read this statement is 1 less than x less than 4, which isn't wrong, but let's think of it differently. Let's think of it as x is a number between 1 and 4. And that's one suitable way in some scenarios to write the answer. In some formats or in some courses, you would stop here and claim to have solved this problem. And in essence, we have. We've discovered if x is any number between 1 and 4, the original inequality is true. Remember in the beginning our two random examples that x could be 3 or x could be 1.4? Both numbers between 1 and 4. But now we've discovered x can be any number between 1 and 4. But rather than use this notation, I like something called interval notation better, where I say 1, 4. By the way, this does not mean the graphed point 1, 4, although it does look like that. This is called interval notation, and what it indicates, with the comma being interpreted as the word through, it indicates that x can be any number 1 through 4. You also may recall from other videos or courses that these parentheses are the interval notation symbol for exclusion. By putting parentheses there, I'm stating that x can be any number 1 through 4, but not 1 and not 4. To prove to you that x cannot equal 1, let's plug 1 into the original equation. Notice I've substituted 1 for x. When I do that and do a little arithmetic, I get a false statement. 3 less than 3 is false. A number can't be less than itself. And since this is a false statement, we've just shown that x cannot equal 1. By the way, by a similar argument, we could also show that x cannot equal 4. And again, that's what the parentheses of exclusion in the answer indicate. Let's now modify this problem by changing it to a greater than or equal to and see what happens. 2x minus 5 is again some number, and the absolute values indicate its distance from 0. So this inequality is saying the distance from 0 has to be greater than or equal to 3. In other words, 2x minus 5 is some number that must be 3 or more spaces away from 0. Let's see what that looks like. Here's 0. Here's one place 2x minus 5 could be, because that distance from 0 is greater than or equal to 3. Here's another place 2x minus 5 could be, because that distance from 0 is also greater than or equal to 3. 2x minus 5 could even be here, at 3, because that distance from 0, which is 3, is greater than or equal to 3. By a similar logic, 2x minus 5 could be over here. That distance is greater than or equal to 3, as is this. And these thoughts all put together lead us to the idea that as long as 2x minus 5 isn't in this zone or this zone here, which would have a distance less than 3, 2x minus 5 must either be in this region here or this region here. If 2x minus 5 is in this region here, then 2x minus 5 must be 3 or higher, which could be represented this way. On the other hand, if 2x minus 5 is in this region over here, then it must be below negative 3, or less than or equal to negative 3. And now that I've represented these two regions as inequalities, I can solve each one of them algebraically using some very simple algebra. This one, I can do all the algebra necessary to isolate the x. And similarly, I could do the same algebra over here and isolate the x there. Now, in some courses or formats, you'd be essentially done. What we've discovered is that x must be less than or equal to 1 or greater than or equal to 4. I'm going to continue, though, because I prefer interval notation. For interval notation purposes, this inequality here can be written or thought of as x has to be 4 or higher. In other words, x can be any number 4 through infinity, including 4 itself. Similarly, this inequality here can be thought of as that x has to be below or equal to 1. But any number below or equal to 1 must be between negative infinity through 1. So those are the interval notation ways of writing this solution. As a reminder, these brackets are interval notation symbols for inclusion. In other words, we're saying that x can be negative infinity through 1, including 1, or that it can be 4 through infinity, including 4. And just to show you why we've put brackets here or included these, let's examine the possibility of x being 1. If I take the original problem and substitute 1 for x, and I do some arithmetic, I find myself with a true statement. 3 greater than or equal to 3 is true because 3 equals 3. And since this statement is true, x equals 1 is a solution to this inequality. And by the same argument, x equals 4 is also a solution. Hence we have the brackets of inclusion at 1 and 4. Now while we technically could stop here with 2 interval notation answers, it's generally considered proper to put those 2 answers together as if they were a single answer. And with the realization that x could be in either of these intervals, we could write the word or in here, meaning that x could be in the left interval or the right interval to make this inequality true. And while that wouldn't be wrong, it is traditional, instead of the word or, to use the mathematical symbol for or, also known as the union symbol. And that one thing in the yellow box is the most proper way to answer this question. Let's turn our attention to problems that are a little bit more messy. In this case, you'll notice that the absolute value is embedded in between a bunch of ugly algebra. And it would be very difficult to make an interpretation of this using a number line right away, essentially because the absolute value is not isolated or by itself like it was in the previous problems. So I think what I'll do first is try to get that absolute value isolated. In fact, sometimes I'll just rewrite the problem with ABS where the absolute value used to be, or even just A. Because by rewriting it this way, it becomes a little bit more clear what we should do to get A by itself. Here's some basic algebra. In order to get A by itself, I'm going to do all of the normal algebra that we would do to solve for A. But here's a reminder from other videos or other courses. Obscure rule for inequalities. When you divide both sides of an inequality by a negative number, you reverse the direction of the inequality. Notice the brown boxes. Okay. But remember, A represented our absolute value. And we haven't solved for x yet. All we've really done is created a simpler inequality that will help us solve for x. By the way, you may not prefer to write A, B, S, or A in the way that I've done here, and you don't have to. The same algebra that I did to isolate A, I could do directly to the original inequality. So let's say I subtracted 10 from both sides, and then to isolate the absolute value, suppose I divided. Recall, whenever we divide by a negative, we reverse the direction of the inequality. Either way, we get exactly the same result, the point being we've isolated the absolute value. Now this doesn't mean we've solved for x. This just means we've created a new inequality that's easier to solve than the old inequality. So now let's go about the business of solving this newly created, shorter inequality. Here's the kind of interpretation that we made earlier. Thinking of the absolute value as distance from 0, and reading this problem as distance from 0 must be less than or equal to 7. If the distance from 0 is less than or equal to 7, then 4x minus 3 must be somewhere 7 spaces or less from 0. Graphically, here's 0. Here is the region of all points that are within 7 spaces from 0. And 4x minus 3 must be in this red zone. In other words, 4x minus 3 must be between negative 7 and 7. And once we've created this double less than notation, we can solve it. In other words, we can isolate x just like we did on a previous slide. So I'm going to add 3 to both sides. I'm going to then divide both sides by 4. I've now isolated the x, and I can now read this statement as a between statement. In other words, x is between negative 1 and 5/2. or written using interval notation, x is all numbers -1 through 5/2. And again, notice the brackets of inclusion indicating that x could actually equal -1 and that x could actually equal 5/2, and this inequality would still be true. Lastly, I'd like to turn our attention to some unusual situations that don't require any algebra at all. For example, this problem looks like one of the ones that we've done earlier using algebra. But I can solve this one in my head, essentially because I have an absolute value on my left side and my right side is a negative number. When an inequality is formatted this way, I don't use any algebra at all. Follow me on this logic. We want to know what numbers x can be. Well, if x is some number, 9x minus 6 is some other number. But the absolute value of any number is positive, regardless of what that number is. So this inequality essentially says that some positive number is greater than -2. But that's always true. All positive numbers are greater than -2. That leads me to conclude that no matter what x is, this is going to be a true statement. In some courses you can write all numbers as your answer, and that simple word phrase, which indicates that x could be literally any number to make this statement true, it would be fine. I personally prefer interval notation, so I'm going to write the interval notation symbol for all numbers, -infinity through infinity. Here's another problem that requires absolutely no algebra, because I have an absolute value on one side and a negative number on the other. The reason I don't need algebra for this is because while I don't know what x is, I do know that the absolute value of anything is going to be positive. So this statement essentially says that some positive number is less than or equal to -4, but there are no positive numbers less than or equal to -4. That leads me to conclude that this statement couldn't possibly be true, and that any number I would choose for x would make this a false statement. And therefore, I can simply say that this inequality has no solution, and without any algebra at all, I'm done with this problem. That concludes the lesson.